For those who are joining for the first time, I Wonder is a science magazine for middle and high school teachers. It features writings about the many dimensions of teaching and learning of science in class and outside it. This magazine is published in three languages: English, Hindi, and Kannada, twice a year. And if you are a practicing teacher, science teacher, we invite you to write for I Wonder. And to do this, you can share your ideas in in about 100 words to I Wonder at apu.edu.in. And if you would like to receive updates of each webinar and a free version of each issue, uh, subscribe to us by following the link displayed in the description of this video. You can also catch us on Facebook. And as many of you know, on the second Wednesday of every month, we invite authors of an article in I Wonder for a live discussion. For today's webinar, we have with us Anand Narayanan, author of the article The Evolution of Stars from our August 2018 issue. Anand Narayanan teaches astrophysics at the Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram, and he regularly contributes to astronomy-related educational and public outreach activities. Anand, thank you for joining us in this webinar.
Thank you, Saurav. Thanks for the introduction. And it's a pleasure to be able to reach out to all the readers, the teachers, and students of I Wonder magazine. So thanks to the Azim Premji Foundation for this opportunity.
Okay, before we start, first thing, is uh, to everyone that welcome to this webinar to all the audience. And I am Saurav Shome, teacher educator in Azim Premji Foundation, and I'm also part of editorial committee of I Wonder, and you all are welcome to this monthly webinars. And as you know, this is a monthly webinar, so we every second Wednesday we organize it, and I will tell you more details about I Wonder at the end of the webinar. And before I start the entire discussion, I'm just putting some of the points here. That here, our audience uh, will listen to kind of responses Anand will give. I will ask him some questions, and he will respond to these questions. And through this process, we'll understand in a greater detail what he has written in his article. And all those who have joined in this webinar, you are requested to type your questions in the chat box. In the last 30 minutes of this webinar, we will try to answer those questions. And Anand, I will put forward these questions to Anand, and he will answer. And so requesting all the audience to prepare with your questions, listen to him, and if you have questions, please type. So Anand, first question I would like to ask you, when we were reading also your article, it is for many of us, we believe that stars are eternal. For example, we see pole stars, we see many constellations, fixed distance stars, and we are seeing it for generations. And that seems that we can find that the stars are eternal. Now, You speak in the article that, like humans, stars also born and die. Stars are also born and die. They take birth and die. So, how did we arrive at this understanding? Uh, So,
Right.
what is your position?
Yeah. So that's a very interesting question. So the idea is that the universe operates at a completely different time scale compared to the human lifetime, and therefore it's not very easy. It's not very trivial to understand how processes unfold in the universe. And in this particular article, I have tried to explain the birth of stars, their evolution, and their ultimate fate. And this entire process from the birth to the death of stars that happens over time scales of millions to billions of years, which is significantly more than the time scale in which even life has been present on Earth. Not to speak about a human lifespan. So, which means that astronomers have to do multiple observations and some very careful thinking to put this story together. And I think a best way to explain this is with the help of an analogy, with the help of a metaphor. So I have some slides here, and if the first slide
Yes.
can be shared,
Yes.
the slide before this. Yeah, so let's assume that an alien intelligent species were to visit Earth on a spaceship. So they land at a random location and they see a crowd of people like this. Okay, they see a number of people and they immediately notice that they all have some similarities. They have two arms, two limbs, etc. They have a head and all those things. And they are also moving around, but they don't all look the same. Some are smaller, some are bigger. So if they keep on looking at this crowd for some amount of time, they will be able to come to this logical inference or conclusion that they are all of the same kind. Only thing is that we are seeing them at different times in their whole life history. Okay, so if by even though this is a random jumble of people, if you go to the next slide, through careful observations, we will be able to put them in a linear fashion. And this is exactly what astronomers also do. We cannot see an individual star taking birth and then generating energy and living its full life for millions or billions of years and then eventually dying. We cannot see that happening in an individual human lifetime or even the lifetime of several generations. But what we can do is we can look at different parts of the universe, different parts of our own galaxy, and look at stars at different stages of their life. In some places, we may see young stars being born. In some places, we would see stars that have been shining for a very long period of time. And in some places, we may see stars that have evolved from their stable phases. And in some places, we will see stars that are dying. So you stitch all these different images together to come up with a story of what happens when a star is born, how do they live their life. So that's how astronomers put this idea together of stellar evolution.
So it seems like you have also given a glimpse of kind of evidences we have to support this belief. Uh, do you think there are any other evidence to, or the kind of evidence you mentioned? This is what is
Yeah,
conclusive evidence.
right. So right from the process of birth of stars, how stars are born, and how planets form around those stars, and all the way up to the death, as I was mentioning, is when we look at different parts of the galaxy, we see the stars at different stages of their evolution, of their journey. So, for example, if I may pull up one more slide, if we can bring the slides back in, and if you
Okay,
can go all the
fine.
way to slide number 21.
Okay.
Let us skip.
So let
Slide
me.
number 21 would be a little bit more further down. Yeah,
Is it?
exactly. Yeah,
Yeah.
this one. Yes. So what we are looking at here is an actual image of a certain part of our galaxy. And in this image, what we are seeing is a huge cloud of gas and dust. So these are generally referred to as interstellar medium, and the densest parts of the interstellar medium would look something like this. And the
Mhm.
densest parts of the interstellar medium is called molecular clouds. Now, when we
Mhm.
look at this molecular cloud in visible wavelength, which is the light that we can see, this is what we would see. Now, if you can move to the next slide, that same region, when we try to look at a different wavelength, this is infrared on the right side image, we see that that same region is sprinkled with the stars. And so, this is one evidence that shows that stars are born in molecular clouds like these. Now, in the visible image, we do not see them because these stars are embedded inside these dense clouds, and the clouds act like a curtain. They don't allow light from these young stars, which are born inside these clouds, to shine through. But infrared light has longer wavelength and it can actually pass through the dust without getting absorbed or scattered. So when we point our telescopes with infrared cameras connected to them onto these regions, we can see through, we can peer through these clouds and we can see young stars that are being born here. So this is how we know that star formation happens in molecular clouds like this. And if you can move on to the next slide, yeah, so here we see several, in each small image, we are seeing different regions of a molecular cloud where star formation is happening. If you can move on to the next slide, 23rd. So, what we are seeing here, this is also a real image of young stars with disks of material around it. And these disks of material are the sites where planets would form around these stars. So they are called protoplanetary disks or circumstellar disks. The names are not important. But what I'm trying to show here is that there are about 20 examples here of very young stars around which we see some disk of material. So what we are seeing are the early stages of formation of stars and the formation of planets around them. So 5,000 million years ago, or maybe 4,500 million years ago, our own solar system would have looked like this for somebody who was there to look at it. In the same way, we see stars once they start shining, there's different stages through which they go, we see in different parts of the universe. So there are multiple observational evidences that allow astronomers to come up with this idea that this is how stars are born and this is how they evolve.
So you actually gave a quite detail of this, and it seems to me that this kind of pictures, this kind of the kind of star forming zones and etc. should be there for long to just look at them because they are so fascinating. So it seems like
Right.
this is our place of origin. So where the kind of terms you have used, for example, you have used a stellar life cycle, and you have mentioned about clouds. So I just would like to know that uh, if you just see that the science in your article also you have mentioned the word stellar life cycle. So scientists use very specific meanings for it probably. But why do they use life cycle to describe this process? Some of your responses are there, the way you have responded, but we want a more specific answer that why do they use such word?
So the use of the term life cycle, when, if you want to talk about the process of birth of stars, their subsequent evolution and death, the reason why it's used is because it is actually a cycle. Okay? So stars are born out of molecular clouds, out of these dense gas clouds that are present in the space between stars, which is called the interstellar medium. So interstellar medium pervades the space between stars, and there are some regions of this interstellar medium which are very dense and very cold. It is in those regions that star formation happens. Now, when stars form, not all stars are going to be of the same mass. Some stars will be born with large amounts of mass, some will with smaller amounts of mass. And how much mass a star has dictates its life. Now, as it turns out, stars that have low mass, our sun is an example of a low mass star. Or if you look at the stars within our own Milky Way galaxy and look at the range of masses they have, sun is not a very prominent star. It's a star with a very low mass. So if you take the examples of stars like our sun, which are generally referred to as low mass stars, they have a particular life sequence. And stars which are much more massive than the sun, they have a different kind of life sequence. So if I were to quickly summarize what this life sequence is and why we use the term life cycle of stars, let me start with low mass stars. So low mass stars like the sun, they live a very stable life, like the way we see the sun right now. It's a very stable star. They live such a stable life for approximately a few billion years. So astronomers have calculated that the lifetime of the sun is about 10 billion years. So billion is 1 followed by 9 zeros. That's the lifetime of the sun. And during that lifetime, there are some nuclear fusion processes that happen in the inner core of the sun, which is the reason why the sun is shining. And similarly, stars of that mass. Now, this nuclear fusion is like a process where energy is generated by fusing lighter and lighter nuclei of atoms together. And so this fusion cannot last for long. It's like, you fill fuel into the in a petrol tank of your car or your scooter, and you can keep on driving it for as long as there is fuel in the tank. So stars also are burning their fuel in their core, which means after some time when they exhaust their fuel, they reach the end phases of their life. So low mass stars reach their end phases about 10 billion years after they are formed. Whereas high mass stars, stars which are much more massive than the sun, they live a much shorter lifetime. They burn their fuel at a faster rate, okay? And as a result of this, they also do not live as long as low mass stars. High mass stars live only for a few million years. It's the same example. If you go back to automobiles, if you have a heavy vehicle, then its rate of consumption of fuel is also going to be large because you have more mass to pull. So in the same way, fuel will be exhausted quicker. So in the same way, high mass stars also live a very short lifetime. When they die, okay, so during the process of their life, they are converting lighter and lighter elements into heavier elements. So this is the nuclear fusion reaction that's happening in their core. For the most part, stars are converting hydrogen into helium in their core. Once all the hydrogen becomes helium, then they continue to fuse helium into heavier elements, carbon, nitrogen, oxygen, etc. And this process continues. And when they reach their end state, the stars die. And this death of these stars is usually visually a very spectacular event. Sometimes the stars explode in a violent explosion, which is called supernova. That is how high mass stars that are very massive, end their life. Low mass stars end their life in a little bit more softer manner by puffing out their outer layers. So whatever be the process of death, what is happening is that whatever chemical elements that these stars synthesized, they are thrown back into the interstellar medium where it mixes with the gas and dust that is part of the interstellar medium. And from this, the new generations of stars are formed. So in that sense, there is a cycle that is going on. Stars are born out of dense regions of interstellar medium, which we call as molecular clouds. They live for their duration of time, and when they die, they give back whatever they acquired from the interstellar medium back into the interstellar medium. Only thing is the chemical composition is now different. Okay? So there is a cycle that happens, and this is why this entire process is called the life cycle of stars.
Right. So while you were responding to life cycle, you have mentioned several other things. For example, you said molecular cloud. So in your article, you have mentioned that cloud of gas that consists predominantly hydrogen. So why do astronomers use the term cloud in this context? So is it similar to the kind of clouds we see in the sky, or it's some other properties that resemble?
Yeah. So that word is used because whenever we use the word cloud, there immediately an image comes into our head, like something that is very nebulous, something that does not have any sharp edges, something that's not very compact. Okay, so this is exactly how molecular clouds are also present in our galaxy. These molecular clouds are not very compact, they are diffuse, they are spread over a large region of space, and so that's the reason why the term cloud is used. And the reason why molecular is used is because the temperature in these regions are so low, typically a few tenths of degrees above absolute zero. So that's very, very low temperature. So the temperatures are so low that atoms combine together to form molecules, and the molecules remain intact as molecules. Okay, so there is molecular hydrogen, there is carbon monoxide, there is carbon dioxide, there is ammonia, and all kinds of molecules which are present in this interstellar medium. And why these molecules are present? Because the physical conditions, the densities and temperatures are such that molecules can exist. So they are diffuse gas clouds, and they are also of low temperature such that molecules can exist. Hence, we refer to them as molecular clouds. In terms of appearance, they do look like the clouds that we see in our sky. Only thing is the chemical composition is very, very different, and the densities and temperatures are also very different from the clouds that we have here on Earth. But morphologically, structurally, shape-wise, they are somewhat similar to the clouds that we see in Earth's atmosphere.
But I was thinking the density of the cloud must be much lesser than the clouds in atmosphere, right?
Exactly. Yeah. So when I said the interstellar medium, molecular clouds have the densest region. That densest is a very relative term. Okay. In once you go into outer space, what we refer to as densest would be even less dense than the best vacuum that we can produce here on Earth. So these molecular clouds have fewer number of atoms in a given centimeter cube or meter cube than even the best vacuums that we can produce here on Earth. So as you rightly said, they are nowhere as dense as the clouds that we see in Earth's atmosphere.
So this is wonderful. So this is so interesting. So when you are saying that it is there, and you also mentioned that there are different molecules, right? But predominantly they are hydrogen. So is it so that predominantly hydrogen is a general case, or it happens in certain cases?
So yeah, so it is predominantly hydrogen among all the chemical elements that we have, which is nicely summarized in the periodic table of elements which we learn in school. The most dominant element in our universe is hydrogen. So hydrogen occupies more than 90 percentage of the chemical elements by mass in our universe. Then there is the next most abundant element is helium, and all the other elements that we see in the periodic table, they are all present only in very trace amounts in the universe. I'm not talking about Earth. Earth is a very artificial environment. Artificial in the sense that Earth is very unlike the rest of the universe. Okay, I mean it is natural. Earth is natural, but I was saying artificial in the sense that what we have here on Earth is an environment that's very different from what is out there in outer space. So, if you take a representative volume of the universe, in that hydrogen would be the most dominant element, followed by helium, and then trace amounts of heavier elements. So, since hydrogen is the most dominant element, the molecules that can form are also molecules of hydrogen. So, H2 molecules. So that is the reason. And all the hydrogen that we see in the universe, they were all synthesized in the very early universe, immediately after the Big Bang, which is what the origin of the universe is referred to as in astronomy.
So while you were earlier response, you also mentioned that these clouds give rise to stars. So due to gravity, they starts pulling the
Yeah.
each other. So how does that happen? What is that? This process is quite interesting, right? So how does
Right.
it happen that something generates from clouds?
Yeah. So when we so this is this answer to this goes into the heart of star formation, which is a very active field of research. How stars form in molecular clouds. So a huge molecular cloud contains enough mass to form millions of stars. People who do night sky observations, people who like to do stargazing, they would know Orion Nebula. In the direction of the constellation Orion, there is a diffuse gas cloud called Orion Nebula. That is one of the nearest star forming regions to us. So this Orion Nebula is a huge cloud complex. It will stretch several light years across, and it will have enough mass to form millions of stars. This entire cloud is not going to collapse. There will be smaller regions within this cloud where certain conditions are met for gravity to initiate collapse. Now, what is gravity doing here? So, if you think about a small region within this cloud, there are individual atoms and molecules that are present, and we know that gravity acts between any two objects that have mass. No matter how small those objects are, there will be a force of gravity between them. So, the force of gravity between individual atoms is going to pull those molecules or atoms together, and once they start pulling those atoms and molecules together, that region starts compressing. So it's like almost like a free fall, like a stone falling on earth. It's almost like a free fall. That region starts compressing, and this compression eventually stops when the conditions at the core of this small fragment, which is collapsing. So the small fragment is collapsing, and the collapse process itself can take about 100,000 years or more. Finally, this collapsing fragment, it shrinks to the size of a star, but it is not quite a star yet. The density and temperature in the core of that collapsing cloud becomes large enough to initiate nuclear fusion reaction. So to initiate nuclear fusion, we need temperatures of 10 million Kelvin and densities that are roughly about 10 times the density of lead. So lead is a very dense metal. So once those kind of conditions are achieved at the core of this collapsing cloud, then nuclear fusion can begin, and at that point, the star is born. Okay, so this, which means in a giant molecular cloud, there will be multiple places where this fragmentation and collapse by under the influence of gravity is happening. Gravity is basically assembling these individual atoms together to make this lump of cloud, which is going to become a star. And when that process happens, usually a disk of material also forms around it, which is what is shown in this artist impression. This is not a real image, what we are looking at right now in the slide. A disk of material also forms, which is where planets form. So I don't know whether I answered your question, but basically gravity does this assembling work, like
Right.
pulling things together. Yeah.
Right. But the kind of numbers you mentioned, these are really astounding, right? The the amount density, and then these are absolutely astounding. So I think we'll discuss more about this later. It seems so. Now, uh, in that case, if due to gravity things are condensing, uh, so is it a continuous process? They will be compressed, still continue. They will continue to compress, and then uh,
Right. So yeah, so it will keep on compressing, and what happens is as this fragmented cloud, the small cloud compresses and becomes the size of what we generally uh, uh, know as the size of a star. it's also getting denser. So you can imagine, if you have some gaseous material, if you are compressing it into a tinier, smaller and smaller volume, it's also getting denser, which means whatever heat is being generated inside by the conversion of gravitational potential energy into thermal energy, that will not be able to escape the object because it is now becoming more and more opaque to the emission of radiation. So that this is why in the core the temperature and density reaches, and once the temperature and density becomes sufficient for nuclear fusion to begin, then lighter nuclei will start fusing to form heavier nuclei, and that process will result in the release of energy. This energy, which is in the form of photons, which also in physicists refer to them as electromagnetic radiation, which is photons only, they will try to escape this newly born star, which means they are going to push the gas that is now part of the star. This push that the radiation, electromagnetic radiation, exerts on the layers of the star, this is called radiation pressure. Now, gravity is trying to compress this. Okay, so gravity is trying to shrink the star further. So gravity is acting inwards, trying to compress it. Radiation pressure is pushing it outwards. And finally, an equilibrium is reached. This equilibrium is referred to as hydrostatic equilibrium. Hydro meaning this is a fluid kind of material and it is in a static position. The outward force exerted by radiation and the inward pull exerted by gravity balances out and the star has reached a stable state. And our sun is a star that is in that stable state, in a state of hydrostatic equilibrium. So even though tons of hydrogen are getting converted into helium every second as we speak in the core of the sun, it's like a nuclear explosion that is happening inside the sun. Okay, but we don't see the sun exploding because of this perfect balance between radiation pressure that is pushing the star outwards and gravity that is trying to shrink it. Okay, so that's exactly what is happening. And the slide number 8 is basically a visual representation. If we have time, maybe we can just quickly show that slide. Slide number 8 is a visual representation of this balance between gravity and radiation pressure. So this is what is shown as a cross section of a star, and inside the red small ball that you see, that is the core where nuclear fusion is happening. So people often have this impression that nuclear fusion is happening inside the entire star. No, it's not happening inside the entire star. The conditions for nuclear fusion are present only at the inner core of a star. That is where nuclear fusion is happening. That is where the energy is generated, and that energy slowly wades its way to the surface, and from there it free streams. So that transmission is what heats up the star. And in the article, I have tried to explain this in a box material. Yes. So those of you are interested, you can go and read about it.
Right. So one very interesting point you mentioned, that nuclear reaction does not take place all over the place. It's the core of the star. It's a very important point. So there is a point you mentioned, that there is a balance of thermal and what you mentioned, hydrostatic pressure, right? Equilibrium, hydrostatic equilibrium. So similar kind of things, is there any other example in physics or in nature that this kind of balance takes place with the opposing pressure?
Yeah, so see, it's basically when we are standing on the surface of the earth, we are exerting a force on the earth is exerting an equal amount of force on us, which is why we are neither going inwards, neither are we pulling ourselves upwards. Okay, so there are a balance between forces that are happening all the time. When we inflate a balloon, for example, okay, there is pressure inside the balloon and there is atmospheric pressure that is surrounding the balloon. They are in a perfect balance with each other. If they are not in balance, if the pressure inside the balloon is more than the ambient pressure, the balloon will expand. And this we can actually see if you inflate a balloon and if you go on an airplane, or maybe if you quickly climb a high altitude, the ambient pressure comes down and you will see that the same balloon, even though you have not blown air into it, the same balloon has inflated in size slightly. That is because the inside pressure exceeds the outside pressure, and so the balloon is inflating. Similarly, if the outside pressure becomes larger than inside pressure, the balloon will shrink. So if you go into a high pressure zone, the same balloon will shrink in size. So there are these balance between forces that are happening in many places. I'm not able to think of any more of everyday examples of this, but yeah, there are many.
Yeah, right. So I think this is very interesting point because most of the equilibriums are due to this. The forces,
Right.
opposite forces are same. So you mentioned that the oxygen we breathe, the calcium in our bones, the iron in our blood, are all synthesized in the interiors of stars.
Right.
And is it true for of some known elements, or it is for all elements? It is true.
Yeah. So except for human-made elements, artificially synthesized elements, which are also part of the periodic table, all the other elements that we see in the periodic table, starting with hydrogen, they were all synthesized in the universe. Okay? And if you look at the periodic table of elements, except for hydrogen and helium, and a little bit of lithium, okay, beryllium, etc., little bit of those light elements, all the other major elements, they were synthesized in the interiors of stars. Now, stars like our sun, which are generally referred to as Loma stars, as I mentioned, in the during their lifetime, they are capable of synthesizing elements only up to carbon, nitrogen, and oxygen. That's what they synthesize. So when they die, what remains is a compact object called a white dwarf. The listeners would be familiar with the term white dwarf. There is a lot of work that our Indian astrophysicist Subramaniam Chandrasekhar has done on white dwarf. The maximum mass a white dwarf can have is called the Chandrasekhar limit. Okay? So if you're not familiar with it, you can look it up. So the central region becomes a white dwarf, and whatever a material is ejected that has carbon, nitrogen, and oxygen nuclei present in it, nucleus of all these atoms present in it. Heavier stars synthesize even more heavier elements, all the way up to the iron. Now, even these white dwarf stars, which are made of carbon and oxygen, they are about 200,000 times denser than the Earth, and they are very small size. If they acquire material from outside, from a companion star, then they can also explode in a kind of supernova explosion. And this supernova explosion is known to be the source of nickel, cobalt, iron, and also elements like silicon, sulfur, calcium, magnesium, oxygen, etc. High mass stars produce iron and many of the iron elements, and even heavier elements are also synthesized in the explosions of stars. So, in a very general sense, we can say that all the elements that we see around us, all the naturally occurring elements that we see around us, including the atoms that make up human body, they were all synthesized in the interiors of stars that lived and died long ago. So that's why in the article I mentioned that much of the iron in our body was made during supernova explosions of stars that occurred long ago and far away. For if you are wearing a gold jewelry, for example, all that gold is made from these kind of explosions that have happened in the last stages of stars. Okay, most of the gold is made by the mergers of neutron stars. I'm not getting into the details of it. So when you take a glass of water to drink, every single water, we know the chemical formula is H2O. So every single hydrogen atom was synthesized in the minutes after the Big Bang, 13 billion years ago, and all the oxygen atoms were synthesized in the interiors of many different stars. All the oxygen need not come from the same star. Many different stars that died even before the birth of the solar system. So when they died, they threw back all these heavier elements into interstellar medium and new stars formed, stars like the sun, and eventually they got incorporated into Earth also. So in form, these elements may change. Sometimes they may be liquid, sometimes they may be vapor phase, sometimes they may be in a solid phase, but the genesis of these elements can be traced back to stars. So this fact is true. And in fact, there is a slide, if you could go to slide number 20.
Okay.
So yeah, so this is a astronomer's version of the periodic table. According to me, all the periodic tables that are printed in school textbooks should be updated with this one, because this shows not just the chemical elements, but also shows where these chemical elements were forged, where these chemical elements were synthesized. So the color coding represents the processes that happened in the universe that led to the creation of these elements. And so there are a lot of gaps in our understanding of how some of these heavier elements came into existence. Our knowledge about stellar nucleosynthesis is not complete. So this is, in that sense, this periodic table, this color coded one, is our best educated guess on the nuclear origins of all the elements. So people can Google this up, the origin of chemical elements periodic table. If you Google it, you will get a version of this, and it shows uh, where these elements came from. So yeah, literally that is true. Okay, so and as I mentioned in the article, the atoms in our left hand and the atoms in our right hand would have come from different sets of stars. So,
So this is interesting. Particularly the different colors and is so fascinating. So you mentioned in the early question, in the previous question, that the trajectory of a star's life,
hmm.
it mostly depends on its mass. Uh, how does it really operates? You gave an answer that low mass and long durations. But how does it
Right.
really work?
Yeah. So, as I mentioned, this if you recollect that slide where we showed gravity trying to compress the star and radiation pressure trying to push it, if you think of a big, massive star, then there's a lot of mass there, which means the gravitational pull is going to be stronger. So, if nuclear fusion has to resist this gravitational pull from all the layers that surround that core of that star, okay, then it has to burn fuel at a faster rate so that more energy can come out and that can push the outer layers. So massive stars therefore tend to expend their fuel, tend to burn their fuel at a faster rate. Low mass star, the pull from gravity, or the crushing force from gravity, is going to be less, and therefore they can afford to burn their fuels at a slower pace. So this is the reason why low mass stars tend to live a longer life and high mass stars tend to live a shorter life, relatively shorter. So when I say shorter, I'm still talking about millions of years for high mass stars and billions of years for low mass stars. And once the nuclear fusion shuts off, then the star goes through many different stages. It's kind of difficult to put all that together into words in a very short period of time. But the one summary slide that is perhaps useful is slide number 4. So that slide number 4 also explains from its origins to its death the life cycle of low mass stars and high mass stars. Yeah, exactly this one. So you can see that stars are born in molecular clouds. Small regions fragment and form stars. It's not that the entire cloud collapses; only smaller regions collapse. Small mass stars, they after they burn, exhaust their nuclear fuel, they become red giants, which means they inflate themselves like balloons, and finally they end their life in the form of a planetary nebula with a white dwarf that remains. So this is how our own sun is going to end its life 5 billion years from now. The total lifespan of the sun is 10 billion years. We are halfway through. More massive stars, they also are, once they expend their nuclear fuel, they become these big stars, and after that, they end in a violent explosion, which we refer to as supernova. What remains is the core of the star. The core of the star can either become a ball of neutrons called neutron star, or it can become this highly enigmatic object which we call as black hole. Okay, and neutron stars are some of the densest objects in the universe. A tablespoon of a neutron star will weigh about 10 million tons. So it's like a star core of a star that is exposed now. It has a lot of mass, but that entire mass is confined to a size that is no bigger than a big city in India. So it's a very dense object. So this is the overall process. Okay. So the size is the crucial factor. What size a star is born with, that is going to dictate what kind of chemical elements will be synthesized in the interiors of those stars, and how long it will continue to live in a stable state, and how it is going to die, and what will remain after it dies, whether it is a white dwarf or whether it is a neutron star or whether it's a black hole.
Right. So, is there any way to predict what or we can say what determines the size of a star when it takes birth from a cloud? So, what determines the size?
Yeah, so that's a very interesting question, and this is one of the unsolved known unknowns in star formation field. If you look at a star forming region like the Orion Nebula, which I showed earlier, Orion Nebula is at a distance of about 800 light years from us. If you look at this Orion Nebula, we see a large number of newly formed stars. If you measure the mass of those stars, which can be done in several cases, you'll find that the mass of these stars that form in a molecular cloud, they fall over a wide range. We'll find that there are many low mass stars, fewer intermediate mass stars, and very few high mass stars. Which means that in general, stars tend to form more frequently as low mass stars like the sun, and only very rarely do we have stars that are 30 or 40 times the mass of the sun. So why does this mass segregation happen? Why is there a tendency for collapsing clouds to form more of low mass stars, fewer of intermediate mass stars, and a very few numbers of high mass stars? Why this happens? This is not very well known. This whole idea is called initial mass function. Maybe turbulence, magnetic fields in these interstellar mediums, turbulence, etc., maybe they have some role to play, but it is not clearly known. So this is one of the active fields of research in star formation domain of astrophysics.
Right. But whatever you were giving responses, these are all big numbers, right? These are really big numbers. So, do we have any idea of what do large and small mean in this context? Large.
Yeah. So that is very interesting. So you mean in the context of star formation, right? Only talking about stars, right? Because otherwise large could mean the entire universe itself, which is the largest physical scale that we can think of. So if it is in the context of star formation, stars, etc., okay, the biggest objects in this entire story of what we are looking at in the slide right now, right from the interstellar medium to black holes, neutron stars, etc., the biggest objects are the interstellar gas clouds, and they have sizes of a few light years. So what that means is, if light were to start its journey from one end of these molecular clouds, it will take them several years to reach the other end, traveling at a speed of 300,000 kilometers in 1 second. So the molecular clouds are the largest regions. A star like the sun has a size of radius of about 700,000 kilometers. So that is still 100 times bigger than the Earth. And stars which are more massive than the sun, they can get as massive as 50, 60, 70 times the mass of the sun, and proportionately they will be also bigger. When a supernova explosion happens, that supernova, I think there is a slide on this. Maybe I'll just, if you can go to slide number 17 and 18. Both are real images of supernovae. Yeah, so what you are looking at here is a real image of a star that exploded. Now it is looking like a very diffuse cloud, but once upon a time this was a star, a compact star, much more massive than the sun, and when it exploded, the exploded material is what you are seeing here. This is a supernova remnant, remains of a supernova. Supernova is basically exploding stars, and this supernova can stretch again several light years across. And in the center of the supernova, there is a neutron star. That neutron star would be of the size of a city in India. Maybe like, I don't know, Delhi or something, a few tens of kilometers across. That's all it is. So there's a huge range in sizes and mass when we
Right.
look at this entire thing. Yeah.
Right. So, once the stars are evolving, the evolution of a star, does the affect the planets that revolve these stars, revolve around it? And what happens to the planets when the star will die?
Yeah. So this planets, since they are orbiting stars, whatever changes that happen to a star is definitely going to impact the planets also surrounding it. So let's take the case of our own solar system. So that since that would be a very personal story, if you take
Right.
our own solar system, life on Earth depends heavily on the energy that is coming to us from the sun. Our entire weather cycle or climate cycles, everything is regulated by the energy that is coming from the sun. Now, sun is right now in a phase, in the longest phase of its life, where it is in a very stable way, it is synthesizing chemical elements in its core. But that scenario will reach its completion or its end 5 billion years from now. And at that point, the sun is going to expand itself into a red giant. And when it expands itself into a red giant, it will be like a balloon that is inflating. The surface of the sun will grow so large that Mercury and Venus will be engulfed, will be swallowed by the sun, and the surface of the sun will come very close to the surface of the earth. So with that kind of a condition, you can imagine that all the atmosphere will be blown out because of the radiation pressure from the sun and because of the enormous heat from the sun. All the oceans will evaporate and life on Earth will become impossible. And when the planetary nebula explosion happens, then at the place where currently there is sun, there will be a white dwarf, a small white dwarf that will be glowing. Okay, so this is bound to happen. How do we know that this is bound to happen? As we mentioned in the beginning of the webinar, we see the same processes happening elsewhere in the universe. We see stars dying elsewhere in the universe. So the death of a star is going to be fatal for planets that are around it, especially if there is life on those planets. Which is one of the reasons why people are saying, in a very futuristic sense, people are saying that the long term survivability of life on Earth depends on our ability to become an interplanetary or interstellar species. We cannot forever remain here on Earth. If we want to preserve life as we know it here on Earth, then the only option is for us to travel into the far reaches of outer space, into other stars, in search of habitable worlds elsewhere in the universe. Because this is eventually going to happen.
So I was really very pessimist when I thought about what will happen to my life after 5 billion years from now. But
Yeah.
now I have a hope that can be there. So this is wonderful. So you mentioned that evolution of a star is tightly linked to the evolution of light. That is very strong point in your article.
Yeah.
And we are literally stardust. Now, would you kindly elaborate this? That how we are stardust?
Yeah. So the idea is that, see, if you look at life on Earth, okay, the life on Earth became possible. So, the people who study the history of life on Earth say that there was something called the Great Oxidation Event that happened 2.5 billion years back, when the presence of oxygen in the Earth's atmosphere suddenly increased, and that happened because of the spontaneous formation of life on Earth. Now, all life on Earth depends on some basic chemical elements. For example, carbon, nitrogen, oxygen. If you look at our DNA, phosphorus, nitrogen, these are all chemical elements that are present in the genetic material that makes us. We are also heavily dependent on liquid water. We breathe oxygen. Plants breathe carbon dioxide. So all these elements, they are cycling within our Earth. But before they became part of the earth, where did they form? Okay, right now I am inhaling oxygen. This oxygen was a byproduct of the metabolism that happened in plants and trees. But where did that oxygen enter those plants and trees? Somebody will say, it went from the form of water that the plants consume. But where did that oxygen and hydrogen in the water come from? So if we keep asking this question, if we keep pushing this thing, then we find that there is no place in the universe except in the interiors of stars where chemical elements that make up life on Earth can be synthesized. So there are stars that were born before the birth of our sun and the planets of the solar system. These stars lived their life, they died, they enriched the interstellar medium with heavier elements. These heavier elements became part of the newly formed newly formed stars, one of which was the sun, and the material that was present around the young sun, which is the protoplanetary disk of which planets formed. So that's why I'm saying when we think about the calcium in our bones and teeth or the iron in our blood, think about all the places those atoms have been. Okay, they have been in the interiors of stars, they have been part of molecular clouds, they have been part of the young solar system, they have migrated within the solar system. So all the individual atoms are much older than our own physical cells or life here on Earth. So in that sense, we are stardust, and the universe is also in that sense within us. Yeah. So I don't know whether I gave enough information on this. Yeah.
It's very interesting. So while you were answering this, I can understand that many of the answers we are getting. So why, and there are so many large numbers and all this. So why do we study questions like this? If someone wonder that is it only due to the just cognitive inquiry, intellectual inquiry, or it has
Yeah.
other implications also?
Yeah, correct. So why do we study astronomy and why do we study things like star formation? So as you rightly said, it is driven by curiosity. So this is a curiosity-driven science. Now, if you look at the hallmark of human species, what is it that distinguishes ourselves from the rest of the living species? Then it is our ability to look at the world around us and ask these profound questions. You know, how did we come into this world? What is the purpose of our existence? What is our relation with the universe that we see? So, from time immemorial, human species have been asking this question. Ever since we looked up at the night sky, we have been asking, are we in some way related to the distant universe, the twinkling stars that we see in the night sky? So it is a curiosity driven science. We cannot help it. You know, we carry this organ inside our head, which is called the human brain, which always provokes us to ask these questions. And the entire scientific history, the history of science, is basically a pursuit to find meaning to our own existence on this planet and our relationship with whatever we see around us. So astronomy is then in that sense curiosity driven. Now, if I may add to what you have asked, are there still questions that are open in this particular field of star formation, stellar evolution? My answer is there are plenty. So what I have described right now are the ideas that have firmed up over the last 100 years of very careful work by a brilliant sets of minds. But there are still many unsolved questions. For example, one of the questions I already mentioned, when stars form, why is it that there is a tendency for stars to form as low mass stars and a lesser probability of them becoming high mass stars? Okay, so this is called the initial mass function, and even now in astronomy, there is no firm understanding of why this is the case. Then, once a star forms, it starts generating energy and it starts putting out this energy into the surrounding media. It starts interacting with the surrounding media. So the energy that is coming from a star, it heats the surrounding gas. There are also particle winds that come from stars. In the case of sun also, there is a solar wind that is propagating from the sun. These particle winds can create shocks in the ambient medium. So these are called feedbacks from star formation. How do such feedbacks affect the subsequent life cycles of stars? Do they aid star formation or do they inhibit star formation? This is not known. Then how do molecular clouds form in galaxies? If you look at our Milky Way, there are a lot of molecular clouds which are potential sites of star formation. But how did these molecular clouds form? Nobody has a clear idea of it. People use computer simulations to try and understand this. And also in the synthesis of heavy elements, there are many open questions. For example, some of the elements like europium, nubidium, etc., people don't know what processes really produces them. So there are still unsolved questions in this, and this is still a very fertile field of research.
So uh, I can understand that you are saying there are many questions uh, that uh, unsolved.
Not answered, yes.
So lots of unsolved questions. So what do you think in a process of science? One idea is to look for principle of falsification. That is, find out some falsifiable
Right.
prediction and test it.
Yeah.
So is it true for astronomy also?
Yes, I think it's very much part of astronomy. Being a discipline of science, it's all driven by evidences. So people try to come up with elaborate theories on how things are happening, and then you have to always back it up with multiple lines of evidences, not just one line of evidence. So this is very much part of the scientific process. So if you now come back to the topic that we are discussing, the nuclear fusion in stars, nuclear synthesis. See, how do we know that there is fusion reaction happening inside a star? We
Mhm.
cannot go inside a star and look and see, okay, there is nuclear fusion happening. It's only happening in the core. And we
Right.
cannot send a probe because the probe will get completely burnt. We cannot get any information. So, how do we know that hydrogen is getting fused into helium, helium is getting fused into carbon? We don't actually have any direct way of looking into the core of a star to see whether this is what is happening. So the way astronomers went about confirming this is, so they looked at all possible ways in which energy can be created in the universe. So, given the conditions that are prevalent in stars, they said, okay, nuclear fusion seems to be the most likely process because stars are made of hydrogen, and we know that in the center of stars, the densities and temperatures are going to be higher, very high for nuclear fusion. So, what kind of nuclear fusion can happen? Hydrogen can become helium through multiple pathways. So people like Hans Bethe, William Fowler, Fred Hoyle, these are all astronomers, nuclear physicists who lived in the early part of the 20th century. They sat down and they calculated all possible reactions, nuclear reactions that can result in the production of helium from hydrogen. And they said that some of these reactions are easier to occur than some others. So this is called the cross section of those reactions or the reaction probabilities. So if there are 100 ways to make helium out of hydrogen, maybe 10 of them are more likely and 90 of them are less likely. So which means those are the reactions that will happen. So they took the likely reactions and they found out that in those likely reactions, if nuclear fusion is happening, then one of the byproducts of the nuclear fusion is a particle called a neutrino. And so they said if this nuclear fission is happening, then a certain kind of neutrino should be produced in the core of stars. So then they went about building detectors on Earth to detect these neutrinos coming from the sun. Because sun is also nuclear fusion is happening. And they found out that indeed, as predicted by the theory, we receive the same amount of neutrino flux as we expect if the nuclear fusion reactions are happening inside the sun. So now your theory is now backed up by observations. So this is how this whole enterprise works. You can come up with a very elegant theory, but the ultimate test of that theory is that it should be supported by nature. So this is happening all the time.
Right, right. So once we see all your answers, it seems these are one is driven by curiosity. Second is they have actually implications in understanding ourselves and nature also. So for some time we are seeing that astronomy chapters, the topic. from grade 9 and 12 is truncated now.
Mm.
Earlier, these were there in school curriculum, 9 to 12, but now these are truncated. So, do you see a value in introducing children to this astronomy, knowing about these aspects?
Yeah. Yeah, that's a very important question. So, let me begin by saying that children are naturally curious about outer space, about stars, etc. So, from a very young age, we see children asking all sorts of questions about what is the sun, what are stars, what are black holes, neutrons. This captures their imagination very easily. Okay? And in terms of astronomy as a subject or as a topic to be taught in schools, see, since children are naturally drawn towards astronomy, it is a great way to introduce physics to them. Okay? By studying astronomy, one can gain a basic understanding of physics, chemistry, mathematics, which are the essential building blocks for most of the specialized fields of study that happens later on. So, if you want to draw students into science, if you want to draw students into physics, chemistry, or mathematics, astronomy is a natural way to do that because anyway, children are curious about outer space. So, as a stepping stone to a career in science or engineering, astronomy can be a great tool. For example, if you want to talk about nuclear fusion, maybe in high school, you can talk about nuclear fusion in the context of what is happening inside the stars, inside the sun. Right? And then you can say that this nuclear fusion, if it was not happening inside the stars, then life on Earth would not have been present. So a very simple idea, a very important idea in physics of nuclear fusion, you have suddenly connected it with ourselves, the emergence of life on Earth. So naturally,
Right.
students will be curious. So how is it? Why are you saying that? Because there is nuclear fusion, there is life. So this gives you a lot of openings to talk about other aspects of science as well. And the second point is that astronomy is a highly interdisciplinary field. So there is a lot of subfields of science, physics that come into topics in astronomy. Physics for sure. Within physics, light, our understanding of light, how we can manipulate light and learn about objects that are emitting light, because astronomy is all about that. You cannot go and take a physical sample of the sun. All the information that we have about the universe has come by looking at the cosmic messengers, which are light particles. So there is a lot of optics involved there, how astronomers carefully manipulate and analyze light to extract information about objects that are emitting that light. There is a lot of gravity, Newtonian laws. If you take our own solar system, Kepler's laws of planetary motion, where again gravity comes in. And we can also tie it up to even biology, origins of life, how it is intimately intertwined with the energy that is coming from the sun, etc. And lastly, this is not just true for school education. Astronomy, if it is properly taught, it can be a great tool for promoting rational thinking and an understanding of the nature of science, which, as you mentioned in your question, also. Okay. So that's also very very important. So the
So,
kind of perspective. Yeah, sorry.
no, I was just going to ask that only. That you mentioned lots of content area, right? That how this can be addressed. Very
Yeah.
good place for interdisciplinary approach. So, and then you mentioned that nature of science. There is a scientific rationality. So, how this can be developed? Any specific examples for it?
Yeah. So see, notions that we have about who we are and what our place is in the universe, that notion can be inspired by many things. It can be inspired by philosophy, it can be inspired by poetry, it can be inspired by folklores, it can be inspired by mythology. Okay, so those are all ways of making sense of our own life. And science is also trying to tell us a story, okay, which is backed by evidence. And the scientific story can be as entertaining, as refreshing, and as liberating as anything else, as music or art or anything. So the scientific process, so this how science arrives at a certain conclusion about the world around us and ourselves in it. That process in itself is so rigorous that the scientific process brings us closer to the truth than probably anything else. Okay, so I'm not saying that the other worldviews are lesser or they are not important. They are all legitimate in their own ways, but science is a successive approximation towards the truth. Okay, so we are always trying to bring ourselves closer. Supposing there is a truth, we are trying to bring ourselves through reproducible, rational processes. We are trying to approximate ourselves towards that truth. So, in that sense, it can be very liberating. For example, just this idea that even though there are external differences among ourselves, one person may look tall, one other person may look short, one may look dark and the other may look fairer, one person may have certain deformities, physical deformity, one person may be very athletic. So in spite of all these differences, if you break it down to the bare essentials, we are all made of the same ingredients, right? So this is a fact. This is not a poetic statement. This is a fact that this is a statement that is backed by enormous amounts of evidence. And so once you bring in this into your perspective, then the whole transaction with the world around us can change if you internalize this message. And jokingly in class, we sometimes say that even a simple act of drinking a glass of water can be a profound experience if you realize that every hydrogen atom in that glass of water is 13 billion years old. So it adds layers of color to our own existence, and this is what science can bring us, and the scientific process can bring us. So, no matter what I would say is that no matter who we are, what fields of work we are doing, not all of us need to be scientists. We can be teachers, we can be advocates, we can be doctors, but it's good to tune into science once in a while and subscribe to the scientific perspective.
Very true. So it seems like that our present is rooted in antiquity, and also it seems that, as you mentioned, I think these are the very fundamental questions, very common questions in many disciplines. We have a common question, that is, what is our origin and what is the origin of universe.
Yeah.
So I think these are the common grounds, but maybe different disciplines have different approach to reach that truth.
Correct.
Now, as you mentioned also about the teaching those to students, so the teachers who are interested in introducing children to astronomy, do you have any idea how teachers can introduce these ideas to students, how they can begin with?
Yeah. So the question is in general about astronomy, right? How to introduce ideas in astronomy to students.
Right.
Yeah. So one advantage is if you want to study physics, and if you want a physics laboratory, you need to have infrastructure for it. If you want to study biology, you need a biology lab with infrastructure. But the laboratory of astronomy is the night sky, which is accessible to all of us. So you don't need any particular infrastructure or particular setup to study the universe. From maybe middle school or even lower primary school itself, we can do many activities that make use of the objects in the sky to understand the changing sky. So in our own I Wonder article, in our own I Wonder editions, we have had articles where we have described how we can have small experiments in class to understand the directions east, west, north, south by looking at the rising and setting of sun. The sun does not always rise in the east and does not set always in the west. So by looking at on an arbitrary day, by looking at sunrise, how do we determine which is exactly east, geographically east, and which is west? We can also understand the phases of the moon and how calendars are made based on the phases of the moon and the motion of the sun around the earth. So these kind of experiments can always be done. We can also give students the task of drawing the positions of stars in the sky on any given time over a period of maybe a month or 2 months or something like that. So most often students and many elders also have this view that stars don't rise and they don't set. That is not true. Okay, so the stars also, just like the sun and the moon, stars also rise and they also set, and that is because of the spin of the earth. So we can ask the students to see where a particular pattern of stars are at a given time on successive days, say 7 p.m. You will find that today the stars are in one patch of the sky, tomorrow the stars are a little more higher, day after tomorrow they are a little more higher, which means that the sky is changing. Even on a given night, as you keep observing the star, you will see that the altitude of those stars change. So a number of experiments can be done, and then there are of course experiments with light that we can do a lot, which can reinforce many concepts in physics and in astronomy. Yeah, so I'm sure there are plenty of online resources available. Our own past editions of I Wonder have touched upon many of these. Yeah.
Right. Right. So it seems like it reminds me like Shah's work that once you are on Earth, but you can know what are the elements in the stars. So,
Right.
so, Anand, do you have any parting thoughts, any concluding thoughts about the
Yeah.
entire?
So right. So, no particular thoughts in general, but overall, I would like to say that this is a astronomy is a very effective way to engage children with concepts in science. Uh, there are many concepts in physics have their applications in astronomy or find there are manifest in astronomy. So you can talk about many concepts in physics by pulling out very exotic and very interesting examples from astronomy. There are numerous such things. If you want to talk about gravity, if you start with black holes, then it is guaranteed that the students are going to be listening to you for the rest of the class. So
Right.
it's going to be very, very interesting. So astronomy is a very accessible science, and there are many popular books that are written on this topic, which reminds me that in the slides I had put on the specific topic of the birth of stars, their evolution, and their death. There are many books that are available, but one recent book, which is written for a popular audience, not just about the origin of stars, but of the origin of life and its subsequent evolution on Earth. That is this book called Children of the Stars, which is in the last slide, slide number 26. Yeah, so if somebody wants to learn more, this is a book written in English. It's available on Amazon, etc. So there are many such accessible books written, and many cities have planetariums available, which is a portal for stretching students' imagination. You go to a planetarium, you see the shows there, and so tune into astronomy, tune into science, and as I mentioned earlier, subscribe to the cosmic perspective, okay, and that it can be a very liberating experience if you internalize. Okay, try to also internalize the message of science. One is to learn science for the sake of examinations, which is what we do on a day-to-day basis. The other is to see how scientific knowledge can change our own view of things around us, our perspectives of things around us. So that is when that happens, when we are able to bring in the scientific perspective, the scientific knowledge into our day-to-day transactions. That is when knowledge becomes wisdom. So our education in schools and colleges should not just be a pursuit of knowledge; it should also be a pursuit of wisdom. So I think that's what my parting message
This
would be.
this is so deep, so deep. So Anand and all of you who have joined us today, uh, thank you very much, and particularly thank you to Anand because you explained it so nicely. And I'm very sure we'll have lots of questions in our mind, and whatever questions if you have in your mind, you can ask those questions to the authors, and for that please send these questions to the email address I wonder at atu.edu.in, and this is available in video description also, and we'll do uh, join you in the next webinar, the 10th of May. 2023. And those who have not yet subscribed to I Wonder yet, we hope that you will do it very soon. And thank you, everyone. Thank you, Anand, again. And we are waiting for
Thank you, Saurav.
questions from you. Thank you.
Thank you, Saurav. Thanks to the I Wonder team and the Azim Premji Foundation for this opportunity. Thank you very much.
Thank you. Thanks.